Good to go? Awesome. Sure. Thank you. Hi, everyone. My name is Denis Ignatovich. And, oh, yeah. Sorry. Am I doing like this? Got it. All right. Hi, everyone. My name is Denis Ignatovich. And let me just open up the right thing here. So I'm with a company called Aesthetic Integration. This microphone is slightly weird. What we do is something called symbolic artificial intelligence. You may also know it as formal verification or formal methods, things like this. But the problem is that a lot of my time I spend right now speaking to venture capital firms and things like this. So you have to be able to take something that you've been doing for like last 5 years and explain it in a single sentence. And it always helps if you can use buzzwords, things like this. So hence the kind of the expression symbolic artificial intelligence. But the gist of it is that we're going to be using, what I'm going to show you today is how we're going to be using mathematical logic to reason about complex systems. And the reason why this is in the context of Xtext is because we want to build nice user interfaces for people to express very complex problems in a way that doesn't require them to actually understand mathematics that's done under the hood. So I wanted to spend a fraction of the kind of the time, first of all, tell you why is it that we're doing these things, what is the kind of the magic under the hood, and then show you what the Xtext kind of wrapper around this looks like, and kind of demonstrate to you that you can have very cool, very powerful automated reasoning technology, such as Imandra, which is the name of our product, but it's going to be pretty useless to general people unless you can build this nice interface for people to express problems that are kind of in a way that's close to their domain. So we actually have this nice 2-minute video that we typically start with. Obviously it has sounds. I'm not sure how it's going to work, so let me just bear with me for a sec.
What's plaguing today's electronic?
Everyone can hear it.
The world economy is built on a staggeringly complex tangle of algorithms. Competitive pressures and economic recession have contributed to increasingly opaque and unstable markets. The effects of glitches and unfair advantages can be devastating, cratering the confidence of investors and ultimately hurting the general public. Regulators and the industry have worked tirelessly to define what safe and fair markets are. What's been missing is a way to analyze and regulate all of the algorithms underlying. The solution is formal verification, the science of correct algorithms. Other safety-critical industries already rely on formal verification to make their algorithms safe. Imandra, by Aesthetic Integration, is the world's first formal verification solution for financial markets. Consider the building of a bridge. A design flaw may be catastrophic. To make it safe, engineers use powerful computer-aided design tools which analyze designs for safety automatically. Powered by latest advances in artificial intelligence, computer science, and mathematics, Imandra brings unprecedented rigor to the electronic financial markets, analyzing the safety and fairness of algorithms before they're deployed. Financial algorithms are unfathomably complex. They can be in a virtually infinite number of possible states. Examining 100, 1,000, or even 100,000 test cases isn't enough. We must consider every possible case to answer definitively what can possibly go wrong. Imandra allows designers and regulators to fix breaches of safety and fairness before they affect markets. Let's build safer, more reliable, and regulatory compliant systems that all of us can trust, saving everyone time and money. Imandra, by Aesthetic Integration, the logic of financial risk.
Cool. All right. So what I wanted to start out with is to kind of show you low-level details of this, the way that our system works, just to kind of give you, let me see this, kind of intuition behind how this thing works. So what you're looking at is something we call IML, which stands for Imandra Modelling Language. This is a subset of actually a French mostly driven language called OCaml. And it is a strict subset with exception of a couple of directives you can see here at the bottom. And what's special about this is that we've given this subset of OCaml something we call formal semantics. So everything that you see in this IML language, Imandra, our reasoning engine, can actually take, and under the hood is going to translate that into axiomatic representation. And what will happen afterwards is going to be treating this code under the hood as a mathematical theorem, effectively, and reason about it in a way that people typically reason about theorems and other mathematical artifacts. So you can think of this as the assembly. So the Xtext component is going to be on top of that, because our users, we don't want them to go and start to learn OCaml. That's not something that's scalable. What we are envisioning is this IML language, and OCaml is the kind of assembly level, and then on top of it, different interfaces for different types of user that are customizable to different domains. So something that's actually cool about what we've done is the language that we built in the Xtext also has formal semantics. And what I mean by that is because everything that you write in that subset of, well, in that DSL that we created with Xtext translates into something that's formal semantics. Therefore, it also has formal semantics. So it's kind of a cool thing. Basically, that DSL that we built is always translatable into precise mathematical logic, which is kind of a cool thing. So, okay, why do we need mathematical logic? Why do we want to care about theorem proving when it comes to language and stuff like that? So, oops, let me just. So this is a fairly technical crowd, so I'm just gonna just go straight into this. So this is our kind of, again, very low level interface, Imandra. So let me do the following thing. So as you can see here, what I've done is define a function sum. Obviously, it's a recursive function. It adds up numbers from 0 including n. So what is sum of 2? 1 plus 2 plus 0. Sum of 10. 55. So IML, in this sense, is just kind of like OCaml interpreter. So it's valid code. What's special about it is we can actually start to verify theorems about it and reason about it symbolically. So you might have heard about this famous kind of story about mathematician Gauss when he was about 5 years old. His teacher told him as a punishment to go and count the sum of numbers from 0 up to 100. So he came back very quickly because he realized there's a formula for that, which is n times n plus 1 over 2. So one way to implement that summation is by using this recursive function. They'll go and do these things. But we also know that that function, anytime n is a natural number, will always equal n times n plus 1 over 2. We know that. So the something that we're focusing on right now is application to finance. And it's critical because you're constantly dealing with systems that can be in what we call infinite amount of states. Right? So it's like you can think of an autopilot software inside a commercial jet. You have so many different possible configurations going into it, going out of it. You want to be able to reason about infinitely many scenarios. Just like here, because n, that can be in infinitely many possible values. It can be 100 million, a billion, all of these things. So what we're going to make is we're going to make a statement about infinitely many possibilities. We're going to say for infinitely many n, that function will always return this number. This is obviously different from testing, because in testing, you can try it for a couple of sample points, but you never really know what you haven't tested. So with Imandra, you can actually write out this thing. So you can, if you just disregard this verify statement, and this is just a special operator that we define, which is a Boolean operator, what you're going to see here is the Boolean function, right? And we're going to ask Imandra to go and verify that this will always hold true. So it comes back very quickly proved and say, okay, well, show us the evidence. And it comes back with effectively a mathematical object, which is a formal mathematical proof. And it tells you that, listen, using induction principles, using rewrite rules, etc., I can actually go and come up with this stuff. So this is exactly how, for example, if Boeing wants to sell a new jet, the FAA will ask them to use mathematical tools and to actually show why certain arguments that they make about safety of their systems are valid. Okay, so that's one example. Another example is, let's say we go and make a mistake. Instead of plus, we put a minus. What would Imandra do then? Comes back very quickly, says, listen, you can actually you need to consider this case, which is n when n equals 1. Okay, great. So another cool thing about it is, let me actually do. What we do is we fully reflect all of these counterexamples and proofs back into the runtime, so you can actually go and compute them and spit them out. So something that I'll show you with Xtext is we're going to formalize a fairly complex piece of people in finance call it specification, but really it's kind of API description. And one of the things that is difficult when it comes to those specifications is people make mistakes. And when we actually go and reason about what they have written, we can come back very quickly with a counterexample and say, listen, you have this, thousands lines of code, but you haven't considered this edge case. And quite often these edge cases are very complex. They can be sequence of many different inputs into the system, and this is obviously fairly trivial. Okay, so by the way, guys, if anyone has any questions, please interrupt me. I want to make this as interactive as possible. So one important aspect of what we're doing is being able to reason about code and being able to verify statements about how certain things behave or find counterexample. That's one thing. Another just as important aspect of it is we can actually reason about, using, again, the same machinery, we can reason about effectively what are the different edge cases of an algorithm. So everyone here, I presume, likes to test their code. People write out test cases, things like this. Same thing happens in finance. And in fact, regulators demand testing. The industry says they're testing everything well. The problem up until now, no one's been able to define what testing means using quantitative description. So what I mean by that is, if let's say we have a production system and we have a spec, what is the quantitative description of all of the features that should be tested about this spec? So we can think about thoroughness in testing. We can say, listen, we generated 1,000 different random test cases to throw the system, but what is the actual quantitative description of the edge cases? So something we can do with Imandra, I think you'll really appreciate. So if I can ask you to consider this function g, again, it's fairly convoluted. There's another function f, and I'll show you something more relevant in an example, but I want to build up the intuition for this. So we've just written a couple of fairly convoluted functions, g and f. So imagine we have to go out and we have to, test how these things are implemented in production. So we have to think about edge cases. And again, the problem is that both of these functions can take x and, actually they're both x's in both times, but they can take integers that have no constraints. So both of these guys take infinitely many possible values as inputs. So we have to take this infinite state space and quantitatively break it down, slice it out into different regions where the behavior is going to be similar. What people typically refer to, if you go to a tester and say, listen, I have this spec, I need to make sure it's test cases, they will whip out their pencil and say, well, let's go through all the edge cases. What I'm going to show you in a second is a machine reasoning about the logic of the algorithm to actually quantitatively describe all of these different edge cases symbolically. So without further ado, so let me just do this. Decompose f. Comes back very quickly and says, listen, I've looked at this function. It can take infinitely many inputs. X was an integer because it deduced a type. And now it's telling us the following. It's telling us the first region is where x is greater than 99. This is a symbolic. Oh, yeah, for sure. Perfect. Okay. So it's telling us within the first region. So basically what you're going to look at is a finite number of regions. And each region is going to have two things. It's going to have a set of constraints that define the input, that kind of constrain the inputs. It's going to have an invariant, i.e. what it expects to always be the outcome of this. And both of these things will be symbolic. So it's going to say that the first instance is x is strictly greater than 99, and the invariant is that the function will always return 100 in that case. Next constraint is x is over 70 and below 99, and 29 is always input. Here this is more interesting because we say it's between 23 and 70, and the invariant is always going to be the input plus 89. So, okay, fine. This is a simple function. Let's also, by the way, let's do test gen on it, test gen f. And what now Imandra is doing, it's taking those regions and actually constraining them and figuring out what is a concrete input that satisfies those constraints. You can actually run this spec on it. And now you can actually use this and say, I have this production system. It has, 15,000 different regions. I'm going to actually go and generate 100 test cases for each region. Right? So this is something we can do automatically. So, okay, fine. The examples here are simple. Let's get closer to finance. Let's get closer to Xtext. I'm going to show you now something which is effectively a formalization of an exchange matching logic. So if you go to, again, I want to walk you through Xtext part, but it makes no sense unless you we build up the intuition why it is needed there. What we're doing right now, what our focus is effectively formalizing the way that people communicate information about how their systems should interact with their customers. So these are effectively financial APIs. So if you go to New York Stock Exchange and you want to figure out how should you send messages there, how should you trade on it, you'll go and find this, 350-page PDF that describes the different rules of this exchange. This, for example, is a specification for Goldman Sachs dark pool. And there are many thousands of these APIs out there, right? And people right now go and manually describe these things in these PDFs, and they say, listen, I have this, test requiring field, and it is conditionally required based on something else, and all of these things, right? So this is how people communicate this information. Finances, the industry spends about $240 billion a year on technology and compliance, and only 25% of that goes to actually new software development. 75% of that is what people refer to as keep the lights on kind of thing. And the reason for that is, if you're a bank and you have to manage, like 5,000 of these PDFs that you're connecting to, because those people are constantly changing this logic, right? And on top of that, you have regulators coming in and saying, well, prove to us that you're connecting to a New York Stock Exchange in the right way. You're not going to do something stupid about it. That's a fairly difficult problem. So what we're doing is we're taking all these PDFs and using Xtext, actually formalizing them. So you might have seen the screenshot that I've shown you before. So effectively, this is a way for you to take that PDF, and we know about the different messages that are possible. We know all of the different types, etc. And so what Xtext produces for us is a state machine representation of this PDF. So it basically knows what the messages, what messages are allowed, what are the different constraints in their fields, and how it can respond to any user. And so the reason for this is we can actually go and automatically say, listen, when you're connecting to New York Stock Exchange, here's 500 different regions you have to consider. This is what you should test, etc. People right now hire extensively to do these things manually, and we're automating this thing. So I wanted to show you another example of, before you go into deeper Xtext questions, I wanted to show you concrete example of formalizing Swiss exchange. So here what we're doing is we're taking a spec like you've seen before, and again this would be the result of us running Xtext generation on it. And we are building a state machine. So you can think of let's say a REST API or a financial specification or API as something that's describing a state machine. So you have certain information that's always contained there, let's say status of your order. You have the different messages that it can accept, and there's certain logic that says how it should respond to them, how it should modify the state if they're successful, or how they should be rejected with an outbound. And then there should be certain events that can happen that are conditioned on the current state of the system. So this is the big thing, is we're building these state machines, and with Xtext we can make that process a lot smoother. So what you're looking at here is an example of Swiss exchange, and I just wanted to show you a much more complex example of doing this region decomposition stuff that I was showing you before. One of the key things when we're discussing exchanges is we have to think about the way that a buy and a sell order if they were to trade with one another, how their price would be calculated. And this information is expressed in these PDFs. In certain cases, it's fairly straightforward, but once you start looking through the little details, it can get fairly complicated very soon. So here, for example, you're looking at a function that's calculating the price of a fill. Fill is effectively a transaction between a buy and a sell order. You can see here we're just conditioning, we're matching on the type of a buy, was it the buy type and the sell type. And if we were to go and think about how many different possibilities, how many different symbolic regions are effectively deduced from this logic, it's going to be a fairly complicated process to do this stuff by hand. What we will do, however, is we're going to ask Imandra to go and decompose this match price. So when we do that, let's see. So again, just loading this from scratch. And as I mentioned before, as it's loading this information, it's going to go and actually convert that to axiomatic representation. And immediately it's spitting out all of these different regions. So these regions can get fairly complicated. You can see here it's saying, listen, when all of these constraints are met, then the variance is the following. This is a bit of a OCaml technical thing, but you can see here it just says that we're looking for the tail of this list of buy orders, and we're looking for the first element. So effectively, this just says that the price within this region will always be the limit price of the second best buy order, right? So that's one way to represent this stuff. And again, we can go and ask Imandra to generate test cases for it. But alternatively, one cool representation would be to, let's just go to localhost. Oops. I think this, I think the resolution is killing our user interface. Okay, so imagine that this is actually being rendered in a nice way. So once we run this function on a decompose function on that logic, we can get basically 103 different regions of that state. So if we look at the first region, which says, listen, here the cells are empty, the buys are not empty, and obviously you're not going to have a fill price if you don't have at least a buy and a sell order here. So it's going to be unknown. Another region, it says, is buys are empty and sells are empty. Again, same reason. Third region is buys are empty and sells are not empty. So again, here, unknown. So all of this stuff makes sense to us naturally. The fourth region is more the interesting example where we can go in and we obviously have a buy and a sell order where I can actually go and drill into these different regions. And this is where stuff gets more interesting. Sorry. This is where the non-trivial examples start showing up. So going back to kind of Xtext, why all of this is here. We can take now a document like this, and this is effectively a description of the API that clients that are trading in this Goldman Sachs dark pool need to abide by. And you can see here there are a couple of things. First is it's using something called FIX protocol. And the FIX protocol is one of many different protocols in finance, but this is the most widely used one. What we've done is, well, there are two parts to FIX. One is what people call session level logic. So all of the stuff that deals with things like heartbeat information, etc., right? Or log on, log off, all of this state management. What we've done is, if you actually go to our GitHub page, you'll find something called FIX engine. So this component, we've actually written it out in IML, and we've started to verify properties about it. So this is open source, all of these things. The second part of these specifications is what people refer to as application level logic. And this is the interesting part. So the session level logic, in theory, should be common to all systems. Everyone should agree on this stuff. Application level logic, this is the customizable part that all of these different effective venue operators, etc., are having to encode themselves manually. And this is what we're using Xtext for. So one of these things that we have to say for is, for example, this exchange or this venue accepts new order single message. And here are all of the different fields to this. What we've done in Xtext is we have taken what are called data dictionary, i.e. the underlying, the protocol mandated message definitions along with all of these types. So going back to Xtext, you can see here that, you know, what you're saying effectively with this is that we're importing this new order single message. And we're actually, because we've generated all of these things under the hood, we can actually tell the user, like, listen, you're missing, let's say, let's just go and, you know, so we know that the protocol is mandating us to actually go in and say, listen, you have to support, you have to have a certain field as part of this message definition. And anytime the user doesn't have that, we'll throw it out and we'll say, listen, you have to support that stuff. So this is one of the nice kind of things. Something else is that you'll see here, there's a lot of this, you know, what are the valid values for all these fields, right? Well, again, we make that very easy. And here you can see this expression kind of language part of this. We're saying, listen, not only do you have this field itself, it has a certain type, but we can actually go and constrain this stuff. So anytime this affects the resultant model doesn't see this, it'll automatically reject the message and will generate that logic. And I'll show you how that's done in a second. You can, you know, we're doing all sorts of cool stuff here as well. You can see you can directly compare price, and price is a float. You know, let's actually, I've never done this before when it's, let's say, not equals. Yeah. So something that we had to do, and again, our problem is that everything that you write, that the user writes in this language that is valid, is translatable into mathematical logic. So this is the big constraint that we have. So, and we also have to make it very expressive. So we cannot allow something that will not, for example, type check under the hood. So something that we had to implement within Xtext/Xtend is, you know, given our background, for us it was a fairly complex type checking system that made it easy for people to express all sorts of complex logic. For example, we have optional types. So you can have something that is none, or you should be able to handle a case where a field is not required, so it can be missing. And for a long time, we thought about, like, okay, well, how do we allow people to have optional fields, but still have logic that references them in a sound way? And we had a couple of experiences, and at the end of the day, we realized, listen, we just have to have optional values, and that's what you see here. And for example, this sum or none. So I can have, you know, none, for example, but I cannot have, you know, this because it's a float. Oops. Yeah. Or something like this. Okay, so this is the kind of, you know, the boilerplate messages. So we understand that the fact that we need to be able to accept messages, and we need to be able to go and reject them when they're missing values or they're just not valid. The more interesting part of this is we actually go and define what we call this the state of this state machine. So one kind of simple example is we send create new order message to this venue. The venue accepts it, and now it has a live order there. So let's say we want to go and buy 1,000 shares of Vodafone within this venue. We have to send in this create new order message with all the valid parameters. It'll go accept it. It'll actually go and then modify the state of this venue. And this is how we represent the state. So we can say here, for example, what is the order quantity? And here we're just saying by default, because it's not optional type, we're saying that, you know, the value is 0, all of these things. And we just have some settings here. And you can see, for example, we had to implement UTC time only and different ISO types here as well. And then, let me just say this. What happens when all of the validity checks are satisfied as part of this message and we actually go and transform the state. We implemented these what we call receive functions. These receive functions, you can see they take this effective type of a message that we can receive, and here we're just going and modifying the state of the venue. And then we're sending out an execution report message with all the various different parameters that will be going out to the customer. This is how, effectively, anytime you have something that's missing as part of this message, we should be able to allow people to handle that as well. And this is how you actually go and send out any reports that have to be sent out, or any state modifications, etc., that have to take place. More interesting parts is when we have to describe what can happen with the state of the venue due to some internal events. So what I mean by that is we go and we send a buy order for 1,000 shares of Vodafone to this venue. It's accepted. We get this acknowledgement message back. But then we have to symbolically say, listen, now you have this buy order of 1,000 shares. You should be able to buy the whole thing all at once. And again, this is all depending on different parameters. But another alternative is you send it in, and then you send it 1 second before the venue closes. And then the next event is that the time change happens, and your order is then rejected, and you have to have rejection message back. So effectively, we have to symbolically be able to describe the infinitely many possibilities that can happen on the exchange side that are constrained by effectively the state of this menu. And the way we do it is first of all, we create these what we call actions, and these actions are symbolic representations of everything that can happen internally. And we say this fill, for example, it can have execution time, all of these things, and it's valid when price is greater than 0, and it's valid when the quantity is effectively at most the amount that you have remaining as part of your order. And together with these, effectively, the way that we're describing state, the way that we're describing the messages and their validity in these, what we call actions, we can actually fully describe this document. And once we press a button, generate, and do this region composition, all of these things, Xtext for us generates an IML model out of this. And it can be fairly lengthy, which we can, do all of the typical thing is, number one, it's executable OCaml code. So we can run it as a simulation environment. We can do it historically backtest that you can put in a production system. Number two, we can actually reason about it, so we can use it to generate test cases, all of this region decomposition stuff that I showed you. So if you're a regulator and you say, listen, show to us how you're connecting to this venue and what test cases you've done for that, instead of looking at this PDF and saying, like, I hired Joe to figure this stuff out, you can actually just go and press a button and say, listen, here's 2,000 different edge cases that I should consider, and here's a report saying that I have in fact done that. So we're very excited because there are so many different PDFs like this out there, and they're all describing effectively things like message validity, state transitions, etc. And by combining the power and the Xtext together with our symbolic artificial intelligence program Imandra, where we can do a lot of damage in this space. So I've been talking for almost 40 minutes now. I want to open it up if you guys have any questions or make it as interactive as possible. Please.
Would this be primarily useful for formal vector development, primarily useful for writing system or basic order?
I think the answer is both. Because something that's special about this, well, if you look at this PDF, the thing is this is in no way actually connected to the production system. So this is a fairly arbitrary, subjective opinion of the person that wrote this PDF. And in fact, if you go through, there are a couple of errors in it. So my background is spent about a decade in trading. Most recently, I ran a central risk trading desk at Deutsche Bank in London. And the thing about finance is most often it's not, the difficult part is not coding stuff in itself, it's figuring out what to code, as I'm sure it is with any, you know, complex kind of projects. And most time people think about this like different edge cases and etc. stuff there. So I think it's one of the kind of motivations for even starting this company is because as someone who was I had to sign off on all of the code changes, etc. And I spend most of my time not even trading, but really thinking about different edge cases of the complex system that we basically created and ran. And as someone that was more of a designer, I was looking for a tool like this and it just didn't exist. So to answer your question is I think it's both. By the way, I'm not an Xtext expert. We have the stuff that I was showing you today, all of the language stuff. We have a couple of pretty amazing guys within AI that have been doing this for quite some time now. And we wouldn't be here without the generous help and support of Sven and the TypeFox family, and Anton has been guiding us through all of the various technical issues. So thank you guys very much for this. Definitely would not be possible without your help. And so, by the way, the reason I said that is I would not be able to answer any technical in-deep questions about Xtext. So I've asked Anton to be here for that. Please go ahead.
Someone placed an order and then the market closed. How is it translated to mathematical variance? Is it made by Xtext, IML, or is it automated?
No, all of this is automatically generated. So great question. Thank you for this. So, okay, what are we looking at here? So let's just try to make this bigger. So let's just take a simple example. What can we analyze? Let's say we have a very small state machine, and we've defined the state as like our current order, quantity, and the current time. So we have three things there. Quantity of our order, how much has been executed, and the time of the exchange right now. We send in a create new order message. All of that stuff gets initialized. The state machine sends us back a reply saying, yes, it's all great. All these things. Now our task is to actually symbolically describe everything that can happen afterwards. Right? So what are the things that can happen afterwards? The exchange shuts down because, I don't know, someone unplugged the system or something from the electricity socket. You can get one fill back. You can get 100 fills back. All of these things. You can have time change event, which will cancel your order because it's expired. So all of these things, right? How do we encode that stuff? So we know that we have encoded already the state definition, the state type definition, the different messages, how we receive them. Then we have, effectively, you can see here are two things. We have type definition for the fill, and here, the way it's translated under the hood is just a type definition. And then we have a sequence of what are called validation clauses. And these are effectively functions that take two things. One is a concrete value of this type, and this is translated under the hood into IML type. A value of a fill, and also a value of the current state of the menu. So it takes two things. And this Boolean statement just tells us whether this fill is actually what we call a valid fill or not. And we can define it for arbitrary effectively validation clauses, things like this. So at the end of it, we'll have the type of our state, global state type of the fill event, and a bunch of validation clauses. The way that Imandra works is you can do all sorts of crazy things when it comes to conditioning. So when just actually going back to, let's go back to this guy. for example, we define this decompose function. I think we're running out of time, but decompose function here, you can see here. Very easily, I can go and say assuming side condition. So I can actually take that function f, and I can actually define this side condition that says x is between 25 and 30, and it'll take that definition and slice it out and say, well, it's actually constrained by those two things. So using exactly the same type of machinery, I can take the type of the state, the current value, all of these things, and I can say, assuming that this action is valid, given all of these n number of validation clauses, give me an example of a value that matches that. And that will immediately go and give us, a concrete example of these things. And then when we're creating decomposition of this stuff, we can actually say, listen, we have, let's say 10 of these transitions, state transitions, whether they're incoming from a user or from internally from these actions. And we know whether they're valid when all of the fields are valid, all of this other stuff that we looked at before, and these validity statements define to us valid actions. So we have these infinitely many possibilities, and we're going to constrain them by all of these validation clauses. And Imandra will actually tell us either, no, there are no actions that are possible that fit this description, or it'll say, listen, here are regions of how the system can behave, and I can actually go and produce to you different test cases, etc. for that. So that's I can show you kind of offline how the decision, but it's effectively this machinery, but just much more complicated. So that's pretty much it. I think we're out of time. I think our hostess is busy with something else, but it's okay. All right, guys. Anyone else? Anything? Yeah, please go ahead.
So formal methods are not tricky to use because sometimes for the user, if you input your data and you change something, like the first time it works and it gets verified, and then you add a few things to it, suddenly the problem explodes in complexity.
Yeah.
And how do you gracefully handle such situations?
Xtext. You have to be able to constrain. So absolutely. So all of these things I can do. If you start in 5 minutes, you can get to states where the problem becomes undecidable. So undecidable is something where you have, out of the space of everything that you can code in OCaml, right? Most things are actually what people are just as undecidable, i.e. there's no algorithm that can actually solve these questions, not even Imandra, but like science cannot answer those questions. On a smaller subset, Imandra can reason about. Even a smaller subset of that is Imandra can reason about automatically with this stuff. So a lot of these things you might require manual input to drive the system in a certain state. What's important is when you're going to domain like this stuff, is not to expose OCaml interface to people and say have a go at it, but really have a well-defined kind of interface, a funnel for which we're using Xtext, and say, listen, here's how we will constrain this problem statement using all of these different things. Make sure it's generated into a valid, obviously IML. Make sure that the language of the DSL itself is very rich and expressive. And under the hood, you can, like anytime some sort of analysis takes a long time, you can actually go and optimize it by writing, custom logic or etc. for these things. But to answer your question, this is why we're kind of doing Xtext, is because we need to be able to constrain the problem in a way that we're the ones that are managing effectively the resulting reasoning that can come out of it, and it's not open-ended kind of stuff, because that would just not scale. And obviously, we'll, in the future, we'll have a community-based stuff where people can write their own, very complicated logics, etc. But the people that write these things and read these things for a living, they have never, most of them do not code stuff. So even asking them to learn OCaml is going to be a long push, let alone anything with formal verification. So. I think that's it. I'll be around here for the rest of the day, guys. If you have any questions, would love to show you this stuff. But thank you very much. Thank you.